Hello and welcome back to a new video. D3D12Ez here on the Ludwig Fusel channel. Now in this video we're gonna continue on our journey towards rendering a image. Now how are we gonna do it today? What are we gonna talk about today? Well, last video we talked about the rendering pipeline and all of its components. Now what you would think is that we're gonna continue on with the first component, the input assembler. We're gonna set it up, use it, and then next video and continue in with the next component. However, we can't process that quickly currently. Why can't we process that quickly? Well, because there is still infrastructure stuff missing. So currently we know how the pipeline works. We have all of our systems and Windows stuff available. However, there are still like parts missing that we need. And this is going to happen a lot of times. I think at least 2 or 3 times it's going to happen that we're going to miss something, that we need something, a new concept, and we're going to learn it for every kind of part of the pipeline that we want to use. Now, in this video, we want to use the input assembler. Let's talk about what does it take to use the input assembler. Let's revisit what the input assembler would do. The input assembler takes data from the GPU memory and assembles a input out of that several locations, maybe like a index buffer, a vertex buffer, multiple vertex buffers, multiple vertex buffer views. It takes all of these informations that are kind of scattered around the memory. It takes all of these informations together and produces a kind of continuous vertex stream with associated data like this is a triangle, this is a triangle, this is a triangle, so that the other parts of the GPU can process it, and that we at the end have a correctly constructed vertex with associations on it. However, there's one big thing in there that we haven't talked about yet: memory. I told you the input assembler takes data from memory. Have we talked about memory on the GPU? No, we don't. So that's what we want to do in today's video. I hope I can put everything in this video how I wanted. I already tried and I failed. So let's see if we can do it a bit quicker without sacrificing knowledge. All right, so how does memory on the GPU works? Well, in general, memory on the GPU is just a pointer, same on the CPU side. CPU side, we call malloc, we get a pointer. GPU side, we call malloc, we get a pointer. Not that easy, however, nearly that easy. On the GPU, it works a bit different because a memory on the GPU is actually associated with a feature, for example, a texture that might need a certain special memory layout, a buffer that needs a certain memory layout, a texture that might need something called multisample anti-aliasing, and there are so many special features and ways to optimize resources on the GPU that a normal malloc would fall short. Next issue that we have is memory on the GPU is in general not accessible by the CPU, right? Because it is on the GPU. It is only connected via a PCIe interface. We can, on the CPU side, take a GPU pointer and access it. It doesn't work. So we also need to have a way to synchronize our memory between the CPU and the GPU side. And DirectX solves that with a very, very unique way. DirectX 12 solves that by defining the concept of heaps and resources. Now, a resource is basically a lot of metadata, a lot of optimizations, a lot of descriptors, and a comp pointer associated to a pointer on the GPU. So for every block of memory that we allocate on the GPU or use on the GPU as a texture or a buffer or whatever else, we always gonna need a accompanying COM object. So if we are allocating memory on the GPU, we need a COM object that manages the reference to that manages the resource state, that might command the driver to put the resource in a certain state to optimize parts of the GPU accessing these memory pointer, or even to put it on the right space on the GPU, because the GPU's memory might be partitioned for optimized access in for certain subparts of the GPU, and this is all controlled by a COM pointer, by a device function that creates the memory block. And this is why we need resources, and why we have a descriptor of the resource, and why we have resource states, and we already talked about that when we talked about the window. Now, the next concept that we need to understand is the concept of heaps. Heap is a location where we want to put memory. Now, generally, a heap on the CPU side, it's malloc. That's the heap and nothing more associated to it. Now on the GPU, it's a bit different. On the GPU, we have multiple heaps, or we can have multiple heaps. In general, it will be always heap memory. In general, heap and heaps, not the same. GPU heap is just a sub-portion of the actual heap on the GPU. There's also a stack on the GPU, but that's something that we're going to talk about when we are going to get to shaders. Now, if we are managing a heap on the GPU, we also need to specify what the heap shall be able to do. So in general, what we can do with DirectX 12, we can create ourselves a manual heap on the GPU and say, all right, this is a heap, create me that heap with that certain size, and that heap shall be used for that purpose. And then the driver can give us a correct pointer to that heap. Now the problem is that in general the GPU does not do memory management for us. So in general, if we would allocate memory on the GPU side, well, we would need to write our own memory allocators and manage that on our own. However, actually, good news, DirectX 12 has come up with a concept of a special resource type that manages the heap by itself. So in general, it of course does not work by itself. It's probably done either by the driver or by the DirectX 12 runtime. I would suspect it's the DirectX 12 runtime, but I'm not really sure if it is the case. However, in general, the GPU allows us, or not the GPU, DirectX 12 allows us to not care about memory management. Now, this is all just talking about memory that's on the GPU. However, the problem is we have still the issue of synchronizing memory between the CPU and the GPU. And how do we synchronize memory? Well, we copy memory by calling copy operations on a command queue. The idea is very simple, right? We're going to put a copy command on the command queue, and then the copying can be done asynchronously between GPU and CPU. It can be serialized, it can be enqueued, it can be handled over the PCI interface. We don't really care about the implementation. We just enqueue a copy operation, what the driver does. It is kind of not our deal. However, since we of course also want to have abstraction, we kind of need to abstract the heaps and resources away from void pointers and resources. So in general, if we want to copy data to the GPU, we first need to put it on a resource allocated on a heap that's not on the GPU, to then copy to a heap that's allocated on the GPU. So the general idea is resources and heap are not fixed to the GPU. The DirectX 12 concept of heaps and resources is not limited to the GPU. Every memory that interacts with DirectX 12 API needs to go through a resource and through a heap. And depending on how we create the resource and how we create the heap tells DirectX 12 where to put the memory. So actually we can create a resource, a DirectX 12 resource that's located on the CPU side but is still a COM pointer. And that's the whole concept that we need to understand. Heaps, resources can be on either side, the CPU side or the GPU side. And we need to make sure that we are creating the resource or the heap on the correct side, on the CPU side or on the GPU side, depending on the purpose that we want to do. And if we want to copy data, for example, our vertex data, if we want to copy that from the CPU side to the GPU side, we first need to allocate a data structure and the associated memory on the C++ side as a void pointer, as a static const array of data, whatever we have as a construct in our C++ application. Then we need to copy it from our application to a D3D12 resource that's accessible by the CPU. And if we have done that, we can then tell DirectX 12 to copy from that DirectX 12 resource to another DirectX 12 resource that is located on the GPU side, and it's used for accessing in our main rendering loop. Now, quite a complicated concept. We're going to tackle it step by step, and you're going to see what I mean step by step. So how do we want to do that? Well, let's get started by doing the whole flow that I just explained to you up here. Now, in general, we want to do it outside of that while function, or that while loop, sorry, not function, that while loop, because we only want to do it once, right? We don't want to copy every frame. Our vertex buffer is gonna be static. It's always gonna exist on the GPU. We just need to copy it once. One time is sufficient. We don't want to waste time doing it every cycle, but we could do it in every single iteration of the while loop, but it would not be wise to do so. Now, the first thing that we need, as I told you, is some data on the CPU side. A plain old classical array, for example. And actually what I'm gonna do is I'm gonna create a const pointer hello. And the const pointer hello is going to contain the text hello world, because actually it doesn't matter what we put on the GPU. We can put text on the GPU, and I'm just doing that so I can later show this to you in inside graphics. Normally you would of course not put hello world on the GPU, and we will also not be able to echo this out on the GPU or see it in in inside graphics, we basically need to know how the bytes look. I'm gonna show this to you later, how this all gets together, but in general, we're gonna put hello world on the GPU. Interesting story. You probably saw nobody else on YouTube or in the world doing that, but I'm gonna do that to you to show you that it's working and how it goes. Now, step 1 is finished. We have some data on the CPU side. Now what we need to do is we need to write this CPU-sided buffer into another CPU-sided buffer that's managed and accessible by DirectX 12. And we do that by creating a resource. How do we create a resource? Well, we ask our device to do so. How do we do that? Well, we're going to get our device. So get device from the context, and then we're going to say create resource. Now, create resource, as you can see, is another madness. We have many functions available. A few of them that's shown here are not resources, like resource sessions and resource views. We don't want to care about them. We just care about resource types. So we have reserved resources, we have placed resources, and we have committed resources. Now, again, madness. What are committed resources? What are placed resources? What are reserved resources? It doesn't matter too much. Committed resource, it is the easy fits all, use once resource that you can use always. You can't optimize with that, you can't use advanced stuff with it, but it works for the sake of using it. And that's what we want to use today and probably throughout the whole tutorial series. Throughout, we might do a bit more advanced memory management where we're not going to use committed resource. Now, the difference between a committed and a placed resource is how it is being allocated on the GPU. A committed resource is allocated by the call that we are doing. If we are calling create committed resource, it's allocated, it's placed, everything is done automatically for us. We don't need to care about memory management. A placed resource, on the other way, needs to be done with custom memory management. So what you need to do is you need to create a heap before you create a resource. So basically say, all right, DirectX 12, give me a portion of GPU memory, for example, like 2 gigabytes. And then you can take these 2 gigabytes and create a placed resource on that. So if you're creating a placed resource, you basically specify the pre-allocated heap and the offset into that heap. And then the GPU is going to put that new resource on that heap that was already pre-allocated. Committed resource is probably doing that under the hood as well. However, it's abstracted away from our concept. Reserved resources are another whole different story of resources. Reserved resources are basically just virtual resources. So you, for example, could create a 64 gigabyte big reserved resource. It would work, it would not fail, and you would also like get a pointer and a range that can actually access the 64 gigabyte big section of memory. However, the problem is, of course, it's not going to be available. There's no GPU with 64 gigabytes of memory available. What you need to do is you need to actually subdivide the 64 gigabyte into small chunks, and then you need to tell the GPU, all right, now I am gonna put that small chunk of that virtual resource, of that reserved resource, onto that physical resource with an actual address that has been actually allocated on the GPU. It is a way of doing custom kind of like virtual addressing with the application. There is a use case for that, for example, like mega textures and stuff like that, but I don't want to go too much into details about these concepts. Just know that it's there, know that it's available, and we might talk about these. I want to talk about so many things in this tutorial series. Let's see what I can do, especially then with like real-time rendering, because many of these stuff is so advanced that it's really hard to deal with that in a tutorial series. All right, committed resource is the way to go. We're going to use the default function, no like fancy 1, 2, or 3 with like fancy parameters, just the default one. Now, as you can see, even the default one does take quite a lot of parameters, but they are actually going to be quite simple, and the most of them are going to be at the default state, right? Actually, 3 out of them are going to be at the default state, and 2 are just going to be referencing the pointer, and we just need to define 2 of them. However, the 2 most complicated ones of them. Now, the first 2 are related to the heap. Now, since we are created a committed resource, DirectX 12 needs to manage the heap creation on its own, and also needs to kind of like know onto which kind of heap it shall put it with all of these optimizations that are available. Now, if you are creating the heap before of that, you don't need to kind of like deal with heap properties or heap flags. However, since we are creating a committed resource, we still need to tell DirectX 12 what kind of heap it shall place that on. The next 3 ones are kind of like describing the resource. It's kind of like describing what kind of resource we want to create with which parameters, a bit of resource state, so what is the initial state to put the resource on, and a bit of how you might want to clear the resource. If you have a texture that is kind of like being populated by a render pass, you might need to clear that resource at a certain point, and you can provide like an optimized clear value for a texture there. Next to IID PPV args, and we have it. It's all done. So let's get started with the complicated one, the heap properties. So what heap properties do we need to define? Well, it's a descriptor, D3D12 heap properties. D3D12 heap properties, HP, heap properties. That's what we want to define. Now, what members does heap property have? Heap property has as a first member the so-called type. What is the type? Come on, give me intelligence, please. There we go. These are the 4 parameters that are available for the heap type. Now, there is a so-called custom heap. A custom heap means that you need to define all of that residentially of the heap. So you need to define if the heap shall be on the CPU side or it should be on the GPU side. Additionally, to your CPU or GPU side, you also need to specify how the access via the PCIe interface shall be planned. Shall the CPU be able to read from that? Shall the CPU be able to write to that? Or shall the CPU be able to not see it at all? You need to define all of these attributes by your own. Now, in general, you could think it's easy, right? If I want to put it on the GPU, I just specify put it on the CPU, on the GPU, and say that the CPU can access it. However, it's not that simple because, well, they are laptops, mobile devices. A laptop has just one portion of memory. There is no GPU. The GPUs might be integrated in the CPU. There might be memory that's dedicated to the GPU. However, it is the same memory. It only has like one kind of memory. And then actually the GPU memory and the CPU memory become the same enum value that you could define later. And that's why we have all of these other parameters. Custom heaps, you should probably never use them. You only want to use one of these 3 default defined like enum values. You have a default heap, a readback heap, and an upload heap. The default heap is placed in the memory so that the GPU can access it and that it has the most optimal use for like in shaders and the GPU operation. Would you use for like a vertex buffer or a texture? The other 2 are kind of like heaps that can be interact with the CPU. A readback heap works in the GPU-CPU direction. So if you, for example, render something on a GPU and you want to copy it over from the GPU back to the CPU, for example, if you're taking a screenshot from your application and you want to save it, then you need a readback heap. You need a readback heap so that you can kind of like copy the data on that readback heap, and then it can be accessed by the CPU to be read, for example, to a file. Now, where this is placed, we don't know. This depends on the driver to decide how it placed it. It could place it on the CPU side, and as soon as you're copying from the GPU to that readback heap, it might go over the PCIe interface, or it might be also stored on the GPU side, and if you're copying from like your back buffer to that, it's a copy on the GPU, and then if you are basically reading it by if you're then reading it with like a mem copy on the CPU side, it's going over the PCIe interface. You don't know. You don't know how it's optimized there. However, it will be optimal for your setup and the driver can decide. Same goes for upload heap, just in different direction, CPU to GPU. And that's what we want to do. We want to copy our hello from the CPU side to the GPU side. So we're going to specify upload because we want to upload data to the GPU. Next thing that we need to specify is the memory pool reference. Now, the memory pool reference is basically the location where the data is stored. IntelliSense, please. Come on. Okay, IntelliSense doesn't like me, so yeah, okay, Visual Studio doesn't like me at all. Let's take a look on this, and let's take a look at this so that you can see what pages or what things are available. Now, the memory pool basically defines where the memory is located. There's L0 and L1. L0 is always like system memory, and L1 is always like the device memory on the GPU. However, as I told you, if you have like integrated graphics and no dedicated GPU and no dedicated VRAM, both might be L0. So in our case, since we are using an upload heap and nothing custom, we're going to set it to unknown because it is unknown from the standpoint of our application. It's unknown, it doesn't know the memory pool, it is filled by the driver. We don't care. Next thing goes for the so-called CPU page properties. The CPU page properties kind of like tell how the CPU can access the memory. In general, on the GPU, it's not available. And on the other hand, you have like write back and write combine. I think write back is for reading and write combine is for reading and writing. Since we are not doing this manually, we're going to also specify it to unknown. And in general, if you're not going to use custom, if you use upload, default, or readback, these are always going to be at unknown. Next thing that needs to be specified is the creation node mask. This is for multi-GPU systems. You can basically define on which GPU the heap is created, so where the memory is basically stored. And then you have a visibility node mask where you're basically going to tell where the memory can be seen from. For example, memory could be allocated on one GPU, but the other GPU might have via SLI access and visibility to that memory. Then you would kind of like define something like, I think it's binary, but I'm not an expert on that. You would kind of like define, yeah, it's created on that GPU, but readable on these. But we're not going to talk about multi-node systems. So we're going to put them to 0, which means use a default 1. Now, as soon as we have specified the heap properties, we can plug them in here. The next thing that we need to specify are heap flags. Now, in general, you could define flags like that it is like a shared heap or shared cross adapters or one of these advanced things up here. Now, in general, you don't specify these advanced ones if you are creating a committed resource. The flags here are just for like stuff like create 0 or hardware protected or shared cross adapter. These are kind of like meant to be used with the create committed resource call. All of these other flags are already specified by the runtime itself. So these other flags are required if you are doing manual management. Then you need to specify something like all buffers and textures or only buffers. These are all things that you need to specify if you're doing manual memory management. However, we are not doing manual memory management. We are using create committed resource, and if you're creating committed resource, 95% of the time you're always going to specify no flags here. So D3D12 heap flag none. If you're doing custom memory management, where I might going to do a video in the future, you need to specify a special value here. But in our case, create committed resource, most of the time you're going to plug in that value. All right, so let's get to the next parameter. Now it's getting interesting, the resource description. So a D3D12 resource desk RD, resource description. Now this one is a bit more complicated, so let me quickly copy all of the parameters over so that we can walk them step by step and take a look at them step by step so that we know what's going to go on here. So it's quite simple. Let me just quickly copy them over. They are not too hard to understand, but there is a bit of conceptual stuff that you need to know. All right, so the first thing that you specify is the dimension of the resource. Now there are like 4 dimensions available that you're going to use: texture 1D, 2D, 3D, and buffer. Now 1, 2, and 3 are kind of like textures. Textures are special types. In general, I always say a texture is an image. However, it's not true. There's also a one-dimensional texture, a one-dimensional image. That's not really possible. However, kind of like a 1D texture is like a buffer, but with the same access features than a normal texture. Same goes like for 3-dimensional textures. It's not the 3-dimensional image where you have like one for the left and the right eye. No, it's actually deeper. So for example, 64 by 64 by 64 would be one thing for a 3-dimensional texture. Also advanced stuff. I don't want to go into textures in general at all. Textures is a concept on a GPU that can do more than an image, but it's always explained as an image very simply. In our case, we want to create a buffer, which means a very basic array of data. In this case, like hello world. So buffer means basic data. Simple as that. The next thing that we need to specify is the alignment. So the memory alignment on the GPU. We have 2 options here. We have the option that we're going to always use, and we have an option for special multisample anti-alias textures. Now the general option that we're going to use is always 64 kilobytes. However, you don't want to specify these 64 kilobytes. There is actually a macro for that I always forget how it is defined. Texture layout. No, I don't want to have a layout. It is something with alignment. I don't know. I always forget these. Let me quickly look these up. Alright, so I found the value that we need to plug in. Default resource placement alignment. This is basically 64 times 1024 just defined as a macro. Yeah, as simple as that. I don't know. I can't remember that. That's really a odd name for macro. Normally you would like think it's D3D12 resource alignment. No, it's called default resource placement alignment. Bit of a naming convention. Alright, so now the next three parameters that are relevant are width, height, and depth or array size. Now, since we are not defining a texture, which would basically mean that if we would define texture, we need to specify width and height, or in a three-dimensional way also the depth, or if we would have arrays, the array size, or if we would have a one-dimensional texture and array, a width and array size, or two-dimensional or three-dimensional. Basically, in general, all of these parameters are going to be one down here. The width is kind of like the width of the buffer, the size of the buffer, and height and depth on the buffers are always going to be 1 because, well, a buffer means plain memory, no like width or height or arrays or depth associated with it, and width is kind of like aliased as the size. It's not a union, could be a union, but I didn't, so we specify it as a width. How big is the buffer going to be? Well, we could try to fit it to the hello world. However, since it's an upload buffer and at a certain point we're also going to move to a certain way of uploading resources, I'm going to move to a certain way of a concept, and I basically just going to specify a placeholder value in here, just 1024. It's sufficient. We don't need to copy like all the data. However, you're always going to have upload buffer that are bigger than your data, and you can optimize these. You can actually fill an upload buffer until it's full and then place all of the copy operations on the queue, and you can overdo it. Can definitely overdo it with how these buffers works and how these upload buffers work. You have the full flexibility. In this case, I'm just going to define like a set size. Now, the next thing that we need to specify are MIP levels. MIP levels is a certain way of accessing textures. Since we don't use it, you could think that we say it to 0 because we don't want to use MIP mapping. No, this is not how it works. MIP mapping is kind of like how often do we want to create a resource. If we are using MIP mapping for a texture, for example, a texture 2D, and we want to use 3 MIP levels, it needs to have 3 copies of the texture in memory. So we would set it to 3. And since the buffer doesn't support MIP mapping, we need to set it to 1 so that we have 1 copy of that buffer in memory. 0 doesn't work because MIP levels is kind of like an iteratable. Probably the runtime is going to go over MIP levels with a for loop and allocating the data there. In this case, we need to set it to 1, and 1 basically means 1 MIP level, or rather to say, no MIP mapping. Even though buffers don't support them. But that's just a stupidity out of DirectX 12. Set it to 1, always, don't think, just set it. Next thing, format. What is the format? Well, the format is only used for textures, right? A texture has a width and a height, so 64 by 64, for example. However, a pixel can be bigger than 1 byte. The format kind of like tells the GPU how wide a pixel is. Well, we are using a buffer, so we don't have a format, so we set it to DXGI format unknown, which basically means, hey, it's no format associated with it. It's a plain old buffer. Also something, just set it to unknown. It's just like this one descriptor that's used for everything, right? That's kind of like the idea. Next thing that we need to specify is sampling. This is used for something called multi-sample anti-aliasing. Now, multi-sample anti-aliasing is also a certain thing that needs to be set in a certain way. You can actually see that these are 2 parameters, count and quality. If you don't use multi-sample anti-aliasing, you're always going to have a count of 1 and a quality of 0. Now, again, same story with like these MIP levels. If you have a count of 1, there is like 1 copy in memory. If you have more than 1 count, it also needs to have more copies. And then you would kind of like indicate more copies by adding the value in here. And the quality is kind of like the quality used for the algorithm or the complexity of the MIP mapping, and not the MIP mapping, in this case, the multi-sample anti-aliasing, the complexity or quality of the algorithm. And since we don't use it, we basically say 0, which basically means disable the algorithm. And by setting the count to 1 basically means, hey, have one kind of like set of pixels available. In this case, like 1 set of our buffer. And same then like MIP levels, we can't set it to 0 because like normally you would say, hey, I don't use multi-sample anti-aliasing. Let's put it to 0 because I don't want to use it. No, that's not how it works. It works like that. You don't use it, you set it to 1. That's the idea. All right. So the next thing that we need to specify is the layout. Another thing on how GPUs optimize it. A texture might not be stored in memory as you think. The texture might be stored in a certain swizzle pattern, it's called. It has something to do with optimized access and how these works, and there's a standard swizzle and an undefined swizzle, and you could also set it to unknown if you don't really care about what's happening, but this is like all not the case that we want to do. This only works for images or for textures. If you don't care about it, you put it to unknown on an image. if you want to have a certain swizzle pattern, you put it either to undefined swizzle because you don't care how it's swizzled, or you set it to standard swizzle to follow kind of like a standard pattern of swizzling. And you kind of like specify what goes. However, on a buffer, you would think, yeah, I'm going to put it to unknown, right? I'm going to put it to unknown because I don't know how the buffer is swizzled. No, that's not the case. Your layout is actually known, because if you put it to unknown, it might get swizzled. And the buffer is not meant to be swizzled, right? The buffer is meant to be first byte, last byte in order. And that's why you need to put it to row major. It's called row major because like it's oriented by rows, and I don't know why it's really called row major. It would also be in order, would also be a nice property, but it's called row major. There's probably a story, an idea behind it, but we need to set our layout explicitly to row major. That's the only thing that makes sense for a buffer, and if you don't specify it, the runtime is going to yell at you, and probably your resource creation is going to fail, or it's going to by default assume that. Row major basically means in order layout. First byte is the first byte, last byte is the last byte, everything in between is done in order. And since we have a buffer, this is the one that we need to specify. Important, 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 just need to be as is. And again, you just need to learn that once. This is a buffer will always look like that, including like that flex that we're going to specify now. The only thing that the buffer really is going to change is the width. And later on, we might also write a class that abstracts this away, right? That's the idea. All right, so the next thing that we need to specify are the flags. Now, what are flags? In general, as you can see, flags are kind of like defining how resources are used. For example, you can define a flag as being cross-adapter, which means that it can be used, this resource can be used across multiple GPUs. You can define it as a render target if you want to render to. That's basically the flag that DXGI used for the back buffer. And if we do rendering to custom resources, we also need to specify that. If we want to allow like simultaneous or unordered access, we also need to specify it. Same for depth stenciling, same for ray tracing stuff, video, decoding, encoding. Like all of these advanced usages have certain advanced flags so that it can be optimized and placed in a certain like memory location or at a certain like state, or to kind of like register it with like certain primitives on the GPU. All not relevant for us since we are having a buffer that's on the CPU side. And later on also a buffer which looks the same than that on the GPU side. And in this case, flag none. We're not going to specify anything. Now we can use that now in here to RD. The next thing that we need to specify is the initial resource state. In our case, it's going to be the resource state common, which is the common state for that certain resource. We don't want to specify a certain resource state, or we might want to, but currently we don't want to provide a certain state, so we're going to put it to common, and it's going to be good. Next thing is to optimize clear value. Well, this one is on the CPU side. It's an upload buffer. It doesn't make sense to clear it at all because the GPU is not going to be able to access it. However, if you, for example, create a custom buffer that you want to render to, you can provide an optimized clear value so that it might keep this kind of like stored in memory, stored on the GPU, and allows you to clear resources a bit more, a bit faster. In our case, we don't specify that, so we're going to put it to null pointer, and we are good. And then we are already done with describing our resource, or kind of like filling our create committed resource call. Now we just need the IID PPV args so that we can fill it. So let's actually create the resource here. Com pointer ID 3D12 resource 2. Let's call it upload buffer. And let's plug it in here with IID PPV args and a address of that, and boom, we are done. Now, long story short, quite simple, and actually it's going to be a pattern. If you're going to create an upload buffer, these are the two descriptors that you need. They're always going to be the same. Always, always, always. They're never going to change for that certain use case. The only thing that's changed is going to be the width to be the size of your upload buffer. But the same, going to be the same. The other parameters. Let's quickly see if this works. Let's click on debug and see what we got. So you can see that the breakpoint was hit, and if I take a look at the left, you can see that I have my upload buffer. It's a correct resource, and boom, DirectX object pointer is valid. We have some information available, so everything is good and nice. Okay, so now that we have a upload buffer, we want to put data on that upload buffer and then put it on the GPU. Now, since we are already talking about resources, I want to quickly also create the same buffer on the GPU side, so the kind of like vertex buffer, because it makes sense, right? Vertex buffer. In general, the vertex buffer has the same properties than what we had previously. vertex buffer. The properties are going to be the exact same properties. The only thing that's going to change is the heap. The heap here is kind of like an upload heap, and the resource was described like that. Well, the buffer on the GPU side for the vertex buffer, it shall be the same than the upload buffer. Well, right, because it's just a simple buffer, it is having the same properties, same size, it all also works on the GPU for the vertex buffer, than like the properties of the upload buffer. The only thing that's different is that we want to have heap properties that are not on upload, but on default. So HB upload is going to be that one. That's going to be renamed here. Okay, we could have used Visual Assist to make this a bit more easier. So HB upload, we're going to change it, and then we're going to duplicate this to HP default. Let's call it default. So we're going to have another heap properties. Now it's going to be a heap property for a default resource. There we go. The only thing that we need to change, since everything else is done automatically, is we need to put it on default. And then we can put default in here as well. And boom, we have now two resources, one created on a default heap on the GPU and one created on the CPU side as a upload buffer. Now, as you can see, everything else, it's exactly the same, and we are good. Make a breakpoint here, run it, and we should see that everything else should, yeah, of course I'm now on full screen. We should now have two resources allocated, and they are both good. The only difference is really that it has one allocated on the GPU side and one allocated on the CPU side. Can we vertify that? Yeah, let's do it, even though the video is long, and with like everything that I do, I make it longer and longer and longer, but that's okay. I think it's important to understand that. Let's quickly recompile it and inspect it in Inside Graphics. Should not be a big of a deal, and of course I forgot to start it as admin. Let's see, maybe it works currently without admin access. Let's see if it gets at me that I did start it as admin. Let's take a look at it if we can collect the performance counter. Looks good for now. So let's do a quick capture and let's go into the UI in here. Let's go to frame debugger and let's go to all resources. And if I take a look at all resources, you can actually see that we have two new entries in here, or it means two entries. These were the ones that we had previously. And now we have two buffers in here, buffer 1 and buffer 2. If you take a look at these, I might be able to see where it is located. State comment, do I see where it is? I don't think that I really see it in this view. Maybe I can see it here. Yeah, there you go. Here you can see this is a upload type, and you can actually see that these are also unknown. It's a bit bad that they haven't been populated, but you can see this is like our upload buffer, buffer 1, and buffer 2 is our default buffer on the GPU. And actually, if I would double click them, you can actually take a look at the data that's in here. So you can see that this is all zeroed out because, well, there's of course no data in here. By default, it's creating them zeroed. You can see the address, the actual GPU address of these. You might be able to tell a bit of a difference between they have different addresses. No, actually they have quite similar addresses and they're actually behind each other. Maybe they have actually been both created on the GPU. Could be possibly be that they are both on the GPU, but this really depends on like the vendor, right? Okay, so in general, we have these two buffers. Let's now do something with them, right? That's the idea. We want to do something with the buffers. Let's terminate the thing here and let's go in and do something with these buffers, right? We want to copy hello world on the buffer. How do we do that? Well, the first step that we need to do, now that we have the resources, is we need to copy void pointer to CPU resource. And then we need to copy CPU resource to GPU resource. Now, how does copying work? Well, copying only works if I can have access to memcopy, right? Or to any other copying function. And to gain access to copying, we need to map our upload buffer. So our upload buffer has a function called map, where we can map a so-called sub-resource. Well, what sub-resource do we want to map? Really like no one, the first one, so we're going to put it to 0. Then we need to specify a so-called D3D12 read range and a void pointer pointer. The void pointer pointer is our target buffer, so void pointer pointer, or just void pointer upload buffer, let's call it address here. Don't really need to specify something. D3D12. How was it called? Range, I think. Right. Yeah, D3D12 range. Let's call this upload range here. And now let's fill in the upload range here. You can see that we have a begin and an end. The begin is going to be at 0. and the upload range at end is going to be 1023. This is kind of like the last element, or better to say size -1. And then what I can specify is the upload range, and I can specify the upload buffer address, and then I should be able to, or I should not be able to, but I should have a address in here that I can copy to. Now, one thing that needs to be called as well, as soon as we are done with it, we need to call the unmap function here, so that we can kind of like say that we are done. You need to specify a so-called written range, so you basically need to tell the GPU, or not the GPU, but DirectX 12, what area of the memory you have written to, so that it can kind of like copy that certain range to the GPU, or synchronize it, or do like whatever it must do with it. Let's quickly make a breakpoint here, and let's see if that does its job. And if we have a buffer available. All right, you can see upload buffer address is a CPU-sided pointer that I could open up in my memory view, which is probably zeroed or filled with random data. Now you can actually see it's zeroed because, well, DirectX 12 memory, it's always zeroed, right? You can see that there are many zeros in here because probably even more like memory in here than we actually need, because it's like a whole heap that has been allocated in the background, but that's really something that we don't care. Now let's memcopy over to that. How can we memcopy over that? Well, basic memcopy to the upload buffer address, and then we need the source. What is our source? How did I call that? I just called it hello. And then let's do the string len of hello, and we also want to copy the null terminator +1. That's basically how I want to copy over to it. And I think we should maybe already been able to see that in inside graphics, at least on that buffer. Let's quickly check if that actually works. Definitely going to do that, and let's see if we can already see it. It might not be there because, but actually it should be. It should be visible in inside graphics, right? If we can access the buffer here. So if I make a frame capture, I go back in here, go to my resources, open that buffer up. Yeah, you can see that there's data on here. Hello world, and okay. Hello space world exclamation mark or whatever. You can see that we have data on here. However, that's not really a big deal. You can see that this is our upload buffer. This might still be on the CPU. It's not a big deal that we can see data on here. What we ultimately want to see is we want to see the data being in that buffer, in a buffer 2 here. We could also name these, but that's not really a big deal if they are not named. We want to see them in buffer 2. That's like the interesting thing. Now, how can we see it in buffer 2? Well, we need to copy it. We need to copy the CPU resource to the GPU resource. And how do we do that? Well, actually, we can only do that if we get a comment list. So you can see comment lists. We handle them in here by a init comment list and then by execute comment list. So basically, what we need to do is we need to have a kind of like constant context like that, so that we have a comment list. Let's call this one pre-comment list so that I don't have a naming conflict. Or actually, we could just do it like that and later on down here do it like that so that we don't have a conflict here. So we could take our comment list in here, and now that we have the comment list, we can call the copy function in here. In this case, we want to copy the buffer region. Copy buffer region is the call that we want to do. You can see that we have a destination buffer that we want to copy to. The destination buffer is our vertex buffer. The destination offset is 0. The source buffer is our upload, not upload range, our upload buffer. The next one is the source offset, and then we have the number of bytes. Number of bytes was string len hello +1, but we can just copy the whole buffer since it's not too big. And that's actually everything that we need to do. Maybe we have a problem. Let's see if we have one. But I'm going to tell you that we do probably going to have an issue here that we're going to solve, but it's not a big deal. Right, copy buffer region, vertex, upload, etc. 0 offset, this is the size, and in general, the idea is should be as simple as that. Let's make a breakpoint here, and let's go to the output, and let's see that we have issues. No, we don't have issues. This is something that can be sometimes, especially if the resource and the usage is simple. You might not have issues here, but sometimes you might. The thing is that our resource is currently in the state common. However, at some point, our vertex buffer will be in the state vertex and constant buffer. This is kind of like the state that we want to have. And if we would directly stage it in that state, you can maybe at some point get an issue, right? In this case, it was ignoring the initial states because buffers are created and used in the state common. With buffers, it is not an issue. However, with certain resource type, it is. In our case, you can see it works. However, in general, the best practice that you want to do is your resources, they shall always start in common. If you want to copy to them, they need to be in the state copy destination. This is a certain state that's actually different than common. Common is 0, copy destination is a special state. And when they have been copied to, you want to put them away back into a different state. In our case, because it is a buffer, a plain old buffer, it actually works. However, just as a simple note, you need to be careful with the resource states. We're going to have a texture at a certain point where we're going to do that, and I'm going to show you how to do it properly. In our case, we are using a buffer. You can see it works, right? And that's okay for this case. But in the future, just to be that you need to be aware, this might not work. Right, so let's compile it in release. And let's take a look if it works on Inside Graphics and that we can see it everywhere. So let's start it again. And let's see, it might actually have not worked, but I think it should work. All right, let's see. F11, what NVIDIA is going to tell us. And if I go to I think it should be open there. If I now go to my buffer 2 and open up my buffer 2, you can actually see that our data is on buffer 2, which is now guaranteed to be on the GPU. And it doesn't seem like much what we have done, or like, doesn't seem to be a big of a deal on what we have done here. However, it is really a big deal what we have done, because basically what we have implemented is we have implemented copy operation from CPU to GPU, and that's important to understand. To sum this up, first thing that you need to do is you need to create your resources. You'll create your resources by specifying a heap or heap properties and a resource descriptor. The heap properties indicate where the memory is being put. So in this case, the type was being upload, and it automatically deduced where to put the memory and how to kind of like make it accessible to the CPU. We done it for upload and default. So one here, the upload buffer, or the upload heap in this case, used for putting data on there by the CPU to then copy it to the GPU, and the default one, just accessible by the GPU, not accessible to the CPU, not used for interaction with the CPU at all, just memory that lives on the GPU, used for actually putting the data in here so that we can later use it and work with it. Resource description describes how the resource is laid out. In our case, we have used a buffer, which gives us certain constraints. The constraints are the alignment, the height, the depth, the MIP, the format, the sample, and the layout. Flex kinda as well, but in this case, just because it's kind of like an upload buffer. And the only thing that's really flexible if we are creating a buffer is the width. In this case, 1024. We use that width to basically indicate how big our buffer is. And then we could create these two resources. And after we have created these, we have done two copy operations. One to our upload buffer by mapping it to a void pointer that we can use. Then memp copying to that void pointer to then do a copy from resource to resource by using a command list. And in general, the idea is this map call will never block because it is memory that's accessible by the CPU. So mapping shall never block or never block too long. So you can directly memp copy. This is basically synchronized. This is asynchronous. Synchronous copy to an accessible range of memory. And then a async copy on the GPU, which we, of course, with these 3 lines did synchronize. But that's not the point here. An async copy from resource to resource. That's the concept of uploading ever. And if you're reading back, the same concept applies but the other way around. You kind of like copy from the vertex buffer to your download buffer, and then you map your download buffer back to memory, and instead of map copying to that map pointer, you are map copying from that map pointer. That's copying in a nutshell. And this is simple copying, and we do gonna implement a damn good system at some point. Not in D3D12Ez, but the video where I'm gonna take the result from D3D12Ez and build it into a framework a very basic framework just covering the features that we have done in D3D12Ez for real-time rendering so that we can do advanced stuff. But that's to be coming later. I've come up with a really nice architecture that we're going to use. I'm still not sure how big it's going to grow, but it's going to be amazing. Stay tuned for that. But in this video series, we're not going to do the advanced stuff. For this video series, this is sufficient. Okay, so thank you for watching today. See you in the next video. Make sure to like and subscribe and have a nice day. See ya. Bye.